Hi, everyone, and welcome to the Habitable Worlds Winter 2021 conference. My name is Chris Irvin Davis, and I'm a research scientist working with Dr. Victoria Meadows and the Virtual Planet Laboratory at the University of Washington. In my research, I use a suite of models to study the habitability and potential for biosignatures in the atmospheres of exoplanets, mainly around M-dwarf stars. In this presentation, I'll be covering interactions between planets and their host stars from a planetary perspective. If you'd like to learn more about this from a stellar perspective, a separate presentation has been prepared by Dr. Julian Alvarado Gomez that focuses on the stellar processes. But if you like planets, you're in the right place. So without further ado, let's get started. So usually when we think about planetary science and planetary processes, we're thinking about the exchange of material between three different layers. The first being the interior, so that would include things like the core and the mantle. The next being the surface, so that's the crust and any ocean that might exist, as well as what is probably the most interesting to astrobiologists at the current moment, the atmosphere. And so some examples of processes that occur between these layers would be things like subduction and upwelling, which transfer material between the interior and the surface. Between the surface and the atmosphere, we might have something like evaporation from an ocean into the atmosphere, deposition of molecules from the atmosphere into the surface of the planet, as well as general surface chemistry. Going directly from the interior to the atmosphere would mainly be outgassing, things like carbon dioxide. But there's one piece of this puzzle that we haven't yet considered, and that would be the star. Now, there's quite a bit going on with the star. It's giving off radiation, it's potentially flaring, and has coronal mass ejections, as well as magnetic activity. Now, all of these things are influencing the atmosphere of the planet, but how exactly are they doing that? Well, that's what I'm going to talk about today. So this diagram lays out the stellar processes, as well as the planetary processes, and how they evolve over time. I realize that this probably looks like an intense web of processes, but I'm going to go into detail about each one of them and explain how they all work. So the main thing to keep in mind is that early on in a planet's evolution, the main process that's dictating the composition of the planet is escape. So that is when you are basically you're losing the atmosphere of the planet to space, and that can vastly change the composition of your atmosphere. Now, the stellar processes that mainly drive escape would include magnetic activity from the star, high energy radiation like X-rays and extreme UV, as well as the stellar winds. Now, these things tend to be stronger during the star's early life, especially its pre-main sequence phase, when the star is still contracting, and the stars tend to be very, very active at that point. Now, later on in the planet's life, the main thing that's dictating the composition of the atmosphere would be photochemistry and less intense particle interactions than we usually see with escape. The stellar processes that are part of that would be flaring, as well as coronal mass ejections and solar energetic particles, as well as far in your UV radiation. All of these things control, but not necessarily control, but impact the chemistry of an atmosphere, the chemistry of the atmosphere of any resident exoplanets. And so I've included a couple examples of how exoplanets might evolve over time here. This certainly isn't a comprehensive list, but they give an overview of how you might start with a planet and end up either in an uninhabitable regime or potentially a habitable planet, which I imagine the habitable planet is probably what we're most interested in here for the purposes of this talk. But in order to figure out how all of these processes affect habitability, we kind of have to lay a groundwork for what habitability is. And I usually try and go by three general rules of thumb. So the first of those would be that you need liquid water to exist on the surface of a planet in order for it to be habitable. Liquid water is essential for life, as we know it on Earth. And without it, life is probably going to have a very hard time existing. So liquid water is the first. Somewhat related to that would be a temperate atmosphere. So Earth exists at what is called a triple point of water, where water is able to exist in solid, liquid, and gas form all at the same time. And that is very important for liquid water to exist on the surface of the planet, but it's also important for the kind of chemistry that takes place on Earth. And the next rule that I tend to go by would be that you need some sort of shielding from harmful radiation like ultraviolet, and shielding from particle interactions. So particles coming directly from the star tend to be very energetic, and if they were to interact directly with the planet here, that could cause a lot of photochemical changes, but it could also cause a lot of damage to any organic molecules and potential for life on the surface. So all three of these things, are things that we should be keeping in mind when we talk about habitability throughout this talk. So without further ado, I'm going to get right into it. And the first process that we're going to be talking about is escape. So escape is a fairly complicated field in and of itself. There are multiple different types of atmospheric escape, but they can generally be separated into two different types of processes. There are thermal processes and non-thermal processes. Very creative. Thermal processes tend to be, they are what they sound like. They have to do with the temperature of the atmosphere and how that affects molecules in the atmosphere. Non-thermal processes include things like photochemical dissociation, ion interactions with the magnetic fields, charge exchange between the stellar winds, as well as ions in the atmosphere, and a couple different ones. So if you'd like to learn more about these, Gronoff 2019 has a fantastic review, as does Tion 2015. I highly recommend you go look at those if you want to learn the specifics of escape. I'm going to talk about a few of these in more detail in this talk. But the first example of escape that I want to go over here is that of desiccation and eventual runaway greenhouse. So basically, you can imagine here for a second that we have maybe a terrestrial sized planet with a thin, dense atmosphere, not unlike our own, and maybe a surface ocean. Now, early on in the star's life, it's very bright. It's giving off a lot of energy. That has the potential to evaporate the oceans off the surface of our planet. And then once that water is in the atmosphere, it can drive the planet into runaway greenhouse. So how exactly does that work? Well, we can do a thought experiment here where we take our own Earth around our own sun, and we see what would happen if we slowly push the Earth in towards the sun. So you can think about this axis as we increase the amount of energy that the Earth is receiving, we are moving through time as we push the Earth towards the sun. Now, first, what we see is that the stratospheric H2O content starts increasing very rapidly. And what's happening here is that as the Earth is receiving more radiation, that heats up the oceans and you evaporate water into the atmosphere. Water is an extremely potent greenhouse gas. And so as it goes up into the atmosphere, it helps trap more heat lower in the atmosphere, which helps evaporate more water. And so you get this kind of runaway evaporation here until all of your water that used to be in the oceans is now in the atmosphere. And so what's happening while that water is being lifted up into the atmosphere is that it's also being photolyzed into hydrogen and oxygen gas. Now, hydrogen being about 8 times lighter than oxygen has a much easier time getting to the top of the atmosphere and escaping to space. Now, eventually what that leaves you with is a bunch of oxygen in the atmosphere, which serves to heat up that atmosphere. And this is why we see this rapid spike in temperature. And once you get to this point, once you lose this hydrogen and you're left with oxygen and the temperature reaches this point, it's basically impossible to go back to what you had before. We think this is something that probably happened to Venus. But this is an example of if we took our own Earth around our own sun. But what would happen if we did so with different stars? So Luger and Barnes 2015 explored this very thing. They also modeled stars somewhat like our sun, but what I want to focus on here is the M-dwarfs, which I've marked here. So before we get to the results here, I want to talk a bit about these inner edge habitable zone limits. So we can see that for smaller stars, or sorry, not smaller stars, for stars like our own sun, the habitable zone, the inner edge of the habitable zone does move over time, but not nearly as much as it does for smaller stars like M-dwarfs. For example, TRAPPIST-1 is about 8% of the mass of the sun, and so we're looking down here for TRAPPIST-1. Now you can imagine that if we were to find, so imagine a planet like TRAPPIST-1e, right? It's probably right in the middle of the habitable zone. But if we were to find that planet here at 1 billion years, then it likely spent around 100 to 200 million years interior to that inner edge of the habitable zone, which means it very likely was in runaway greenhouse for that period of time. And in Luger and Barnes 2015, one of the simulations that they did was that they took one Earth mass planet with one Earth ocean, one terrestrial ocean of water here, and they put these planets around stars of different masses to see what would happen to them over the course of 5 billion years. We can see here that about over half of these planets end up losing their entire oceans over the course of 5 billion years. And even more of them build up hundreds of bars of oxygen here. And so you can imagine that this is probably not a great situation for life to exist in. There's no water and it's very hot. That knocks off two of the rules that we put forth for a habitable planet. So the next process that I want to talk about would be what would happen if instead of considering a terrestrial planet with a thin atmosphere, what would happen if you had maybe something like an ice giant, like a Neptune-sized planet that has a rocky core, but also has a large hydrogen helium envelope? Would that same process that destroyed our planet beforehand, these same processes that destroyed our planet beforehand, blow off this hydrogen helium envelope and create a terrestrial core that may or may not have a thin atmosphere like our own Earth does? Well, Fulton 2018 used a combination of Kepler and Gaia data to further resolve a planetary radius gap that they had presented in a previous paper in 2017. This planetary radius gap separates out two different populations of planets. The first being a population of super-Earths, and the second being a population of what are called sub-Neptunes. Now, Fulton 2018 posits that this radius gap in these two populations are evidence of photoevaporative escape. So basically, in that scenario, you have all planets early on in their formation starting out with a primordial hydrogen helium envelope, and cores, the rocky cores that are too small end up losing their hydrogen helium envelopes and becoming super Earths that may or may not have a smaller atmosphere, a small dense atmosphere like our own planet. And the rocky cores that are large enough will be able to hold on to and retain a decent amount of their hydrogen helium envelopes, creating something like a smaller version of Neptune in our own solar system. And so in terms of habitability, these sub-Neptunes aren't necessarily great. Due to the hydrogen and helium envelope, the pressures and temperatures down at the surface are extremely high, and it's also very difficult for if any light to get down to the surface for a biosphere to exist. On the other hand, if this evaporation process takes place, if it were to take place over the span of the star's early life, and this hydrogen helium envelope were to evaporate as the star calms down, we could be left with a terrestrial core that may have an atmosphere after the star calms down. That's a much better scenario for life to exist, at least as we know it. Additionally, Fulton 2018 found that the planetary radius gap was dependent on stellar mass, with smaller stars usually creating smaller planets, and the planetary radius decreasing as a function as stellar mass decreases. To that effect, Owen Mahanti 2016 explored what Earth-like planets or Earth mass planets might look like if they were to have a primordial hydrogen helium envelope. So in this example that I'm showing here, they simulated a couple different about Earth mass planets with a hydrogen helium envelope that had a mass that's 1% of the core mass. And so we can see here that with a one Earth mass planet, that the hydrogen helium envelope does decrease by a bit, but it is not completely lost by 100 million years. And at about 0.8 Earth mass, so 80% Earth mass, that hydrogen helium envelope does disappear over the course of about 10 million years. So in order for the process that I just described from Fulton 2018, in order for that to happen around M-dwarfs, it's very likely that planets in the habitable zone of these stars need to be about an Earth mass or less for them to have a chance of losing their primordial envelopes. As I said before, these kinds of planets are probably not great for habitability. Well, these are potentially a better case scenario. It's not a given that these will be habitable, but it's certainly better than if we had a large primordial envelope. The next process that I want to talk about is how the star's magnetic field, along with the stellar winds, can actually accelerate atmospheric escape. Now, in our planet, we're very lucky that our magnetic field shields us from most of the stellar wind. It really only interacts with the stellar wind at the polar caps. But there's been work that shows that that is not the case for all stars and all planetary environments. So, Vadato 2013 analyzed the magnetic environments of 15 different M-dwarf stars. And here in this plot, we're basically looking at if we were to take an Earth analog planet that had an Earth strength magnetic field, and we were to put it around these M-dwarfs, what is the absolute closest it could be while still retaining an Earth-sized magnetic field? So if we were to go closer than these limits, then the magnetic field of these planets would be further compressed and potentially interact more with the stellar winds. And so we can see that here for M-dwarfs, which are basically this region right here, the present day Earth, if we were to have a terrestrial planet with an Earth strength magnetic field here, they would likely, the magnetospheres of those planets would likely be far more compressed in the habitable zone. So what happens when those magnetic fields, when the magnetic environments of those planets, at those planets become very strong? So that was explored in Garofalo 2017, where they studied the magnetic environment of the TRAPPIST-1 star and the 7 planets around it. So we can see here, this plot on the top left is showing the stellar wind density normalized to that of the sun at Earth's radius, so 1 AU. And we can see that the stellar wind density is quite a bit higher here, but what I want us to focus on is this gray surface. So this is the Alphen surface. which describes where the Alfvén number is unity. And so if you'd like to learn more about the Alfvén surface, the talk that I mentioned earlier by Dr. Julian Alvarado Gomez will talk more about the Alfvén surface. But as far as it goes for the planetary environment, what we're looking at here is that the total pressure, which includes pressure from things like the stellar winds, as well as the magnetic field, is extremely variable around stars like TRAPPIST-1. These planets are so close into their star, and the stars, TRAPPIST-1 is still very magnetically active. And so these magnetic environments are very volatile. And so in specific, we can look at TRAPPIST-1F here, which is this purple line, as that corresponds to this simulation right here. So this is a magnetohydrodynamic simulation of the TRAPPIST-1e environment if TRAPPIST-1e were to have an Earth-like magnetic field. And so all of these red lines are showing magnetic field lines coming from the star and interacting with the magnetic field of the planet. And you can kind of see it here. All of these magnetic field lines coming from the star are connecting directly to the magnetic field lines of the planet here. And I should note that here, these arrows refer to the sub and super Alfvénic regimes. So within the Alfvén surface, these planets are subalfvénic, and outside of them, the planets are super Alfvénic. So this plot right here, or this simulation, corresponds to inside the Alfvén surface, and this corresponds to outside. However, the main thing that I want us to focus on here is that these magnetic field lines for the star are connecting directly to those of the planet, which means solar energetic particles and ions coming from the star are able to travel directly along these lines and into the atmosphere, which is actually able to accelerate escape processes rather than helping to protect the planet from escape processes. But how exactly does that work? Well, Garcia-Sage 2017 studied the ionization and heating rates of a Earth-like planet if it were to be in the location of Proxima Centauri b. So we can see here that in general, the ionization rate and the electron heating rate for our Proxima Cen Earth are orders of magnitude higher than they are for modern day Earth. What that means is that there are a lot more ions in the upper atmosphere, a lot more ions and a lot more electrons to interact with the magnetic field lines that we were just talking about in the slide previous. Garcia-Sage 2017 also notes that one of the main things controlling ionospheric outflow, which is the escape process here, at play here, one of the main things that controls it is the temperature of the thermosphere. They also note that there are a lot of variables and uncertainties that go into determining the thermospheric temperature. And so they decide to model a handful of thermospheric temperatures that are multiples of our own Earth's average thermospheric temperature. Now, we can see here that in this plot in the bottom right, the mass loss rates and the overall loss time to lose the entire atmosphere does change as a function of how much of the planet is quote unquote openly interacting with the magnetic field lines. So you can imagine this as we move, as we go lower in degrees invariant latitude, we are basically increasing the size of the polar cap area that is directly interacting and pulling in the stellar winds to interact with the atmosphere. The work from Grafo 2017 as well as Dong 2017 do suggest that for lower mass stars such as Proxima Centauri and TRAPPIST-1, that the open fluxes are more probably what the magnetic environment looks like. So here we can see that if our Proxima Centauri Earth were to have the current temperature of our thermosphere, we're probably looking at about a 5 billion year lost time. So over the course of 5 billion years, there would be enough magnetic interaction, enough ionospheric outflow due to the magnetic interaction showed in the previous slide to lose your entire atmosphere. But if the thermosphere temperature is 4 times higher than it is for our own Earth, we're looking at loss rates of about 100 million years, which is relatively quick in terms of planetary evolution. So you can imagine that an environment like this would probably not be great for life to exist. It takes quite a while for life to evolve and to grow to an extent where we may be able to detect it. And if 100 million years in, you completely lose your atmosphere, life's not going to be able to make it. So now that we've talked about a couple different types of escape and how the star's activity impacts that, I want to talk now about photochemistry and coronal mass ejections and how these things impact the composition of the planet once the star has calmed down. So the first bit that I want to talk about would be how flares, flares and coronal mass ejections, as well as solar energetic particles, can impact the composition and evolution of planets later on in their lives. One thing that Dr. Alvarado Gomez goes into in his talk would likely be that the difference between flares and coronal mass ejections are that flares are entirely a radiation event. So there are no particles in flares. That's just high energy radiation being emitted from the star, while coronal mass ejections are accelerated plasma that is broken off of the surface of the star due to magnetic line interactions and travels outward from the star. So Seguro 2010 goes into what happens when both of these, both flares and flare and particle events impact an atmosphere. So in this plot in the top left here, we see a flare from 80 Leo, which is a very well-studied M-dwarf star, impacting a modern Earth-like planet. So we can see here, this axis shows the fractional change in the ozone column depth. And we can see that by the flare end, the ozone column depth, due to just this electromagnetic flare, the ozone column depth only decreases by about 1%. And then it jumps up to about, after the flare, it jumps up to about 0.5% more than it was originally before evening back out. Now, when they included a particle event with the flare, the results changed pretty drastically. We can see here that the initial flare here does alter the ozone column depth a bit, but what is causing the vast majority of the loss of ozone is the particle event. So at maximum ozone depletion, which happens a little over 3 Earth years after the flare and proton event, we basically see a 93% reduction in the ozone column of this atmosphere, which, oops, my bad, which probably is not a great environment for life to exist in, but we'll talk more about that next slide. So there was another study done following up on the work of Seguro 2010. So Tilly 2019 explored a very similar parameter space using a flare frequency distribution from a different star. But the meat of it is basically the same, where we see here, these are the mixing ratios of various molecules in the modern Earth atmosphere. And each one of these cases has the planet being inundated with flares of varying energies at different rates. But in all of them, we can see that the ozone, which is shown in red here, that the ozone mixing ratio changes or decreases by over 2 orders of magnitude between the initial state in the atmosphere and maximum ozone depletion. I should also say that these flares do include particle events, and so that's this matches up with the Segura 2010 results, where including flares does vastly deplete ozone in the atmosphere. Tilley 2019 also showed that at the maximum amount of ozone depletion in the atmosphere, the amount of UVC and UVB radiation that's reaching the surface of these planets increases drastically and can increase pretty drastically. And so we know that UVB and UVC are pretty harmful to the formation of organic molecules and let alone life. And so if a planet is being inundated by flares at this frequency and of this magnitude, flares and particle events, that would probably not be such a great picture for life. So now that we've talked about flares and coronal mass ejections, I want to talk a little bit more about how far and near UV radiation can impact the photochemistry of a planet, as well as its ability to be habitable or interpreted as habitable, or to create a bad environment for life. So if the planet is able to self-shield from the strong UV radiation, it's more likely to be habitable. You're more likely to be able to form organic molecules. If the planet's not able to do that, it's pretty likely that even though you have an atmosphere and it may be temperate, you may end up with a planet that is completely devoid of life. So how exactly does this work? Well, Segura 2005 was the first paper to really explore how UV radiation from M-dwarfs, which tend to be more active in the ultraviolet than stars like our own sun, and how that elevated UV activity impacts the composition and the photochemical processes that are happening inside of the planet's atmosphere. So we can see here that the temperature profile of stars around M-dwarfs changes by quite a bit. There's no cold trap here. The stratosphere is isothermal before it starts dropping off. But the main thing that I think we should focus on here is that the ozone abundances don't change all that much, maybe by a factor of 4 or 5. So we're not talking orders of magnitude here. But conversely, the methane abundance in the modern Earth around these M-dwarf stars is well over 2 orders of magnitude above what we see in the sun. Above what we see in the sun. And so we see that in this thermal emission plot here, where the 80 Leo planets spectrum has a much, much stronger methane feature here, while the ozone feature is basically, it's a little weaker here, but it's basically just as strong and just as detectable. And the reason this is important is because it's long been held that the simultaneous detection of a oxidizing molecule such as ozone or oxygen and a reducing molecule such as methane would not be able to exist in an atmosphere at levels that are able to be detectable. That if there's a lot of reductants, there shouldn't be a lot of oxidants, and vice versa. So if we were to detect these things simultaneously, that's good evidence that there is some other source of these molecules on the planets, in the planet somewhere. And so it basically it constitutes a biosignature. And so this study basically showed that the O2, O3, and methane biosignatures are easier to detect around M-dwarf stars than around stars like our own sun. Another paper that built off of Segura 2005 was the Rugheimer 2015 paper. Here they use a spectrum of 80 Leo, again, which is a very well-studied M-dwarf star. They use a spectrum of 80 Leo along with a scaling relationship to create spectra of, to create model spectra of M-dwarf stars all the way from M0 to M9. And then they use the photochemical model to study how the varying amounts of UV flux from these M-dwarf stars influence photochemistry. They also used spectra from the muscle survey, which are semi-empirical spectra, to compare to their models. So we can see here that as we go from M0 to M9, so these would be larger, hotter stars to smaller, cooler stars, we can see that there's a fairly monotonic progression in the concentrations of things like ozone and in methane. So for the hotter stars, there tends to be more ozone, but less methane. And the opposite is true for these cooler stars here. We see some of the same behavior with the semi-empirical muscle spectra. It's a little more complicated for ozone, and these are moving around a bit more. But for methane, we do see it's not linear, but it is a monotonic, I suppose, regression of the methane mixing ratio. So as in general, this plot is showing that the ozone abundance decreases with as the spectral class increases. So as we're going from hot stars to cool stars, ozone is decreasing and methane is increasing in concentration. And what that means for detection is it's a combination of things. So the relative amounts of ozone here, so the amount of ozone that is in the atmosphere of the planet around this cool star, which is the black line, does have an effect on the strength of this ozone feature. But the main thing that is controlling the amount of reflected light here is the star itself. And so for these hotter stars, these M0s, they give off more radiation in this wavelength range where ozone is absorbing, whereas the cooler stars, their peak blackbody radiation would be shifted more over here. And so they give off very little radiation here. And so this feature would be very difficult to detect for stars like TRAPPIST-1 and Proxima Centauri, but much easier for early type stars, for earlier type M-dwarfs. In a similar but opposite way, the methane features are stronger for these smaller stars, partially because the mixing ratio of methane in planets around these stars is higher, but also there's more radiation from the star at this point, in this wavelength range. And so this has actually laid the groundwork for the work that I'm doing currently with the Virtual Planet Laboratory. And so we're working with a team at ASU headed by Dr. Evgenia Shkolnik. And her team use the Phoenix stellar atmosphere model to produce high resolution spectra of these 5 different M-dwarfs here. And then we at the Virtual Planet Laboratory take those spectra as inputs to our coupled photochemical and climate model to create a self-consistent planetary atmosphere that's consistent with the radiation coming from the star. And so we do this for 2 different types of atmospheres for each one of these stars. We do a pre-industrial Earth as well as an Archean Earth. Both of these planets have 10% CO2 because that is what is required to keep the planets temperate when they are receiving 66% of the modern Earth's energy input from the star. And then we use these self-consistent cases as a basis to test how UV radiation changes across spectral class, how it changes through age, how Lyman alpha changes. We basically use these self-consistent cases as a test bed for testing how UV radiation changes and how that influences the composition of these planets. And so the results that I want to share with you today have to do with how UV radiation changes across spectral class, as well as how it changes as the stars age and their activity levels change. So the first result that I want to share is that of the spectral class. So here we see our 5 different M-dwarf spectra, and you can see that the amount of UV radiation can change by about an order of magnitude here in some places. But another important thing to keep in mind is that the ratio of far UV, which is this region over here, to near UV light, which is this over here, changes as a function of spectral class. And so both the the overall amount of UV flux, as well as the ratio of these 2 types of UV, both of these things impact how gases in the atmosphere are photolized. So we can see here some cross sections of interesting molecules in our atmosphere, and we can see that their cross sections are fairly complex in UV space. And so we need models to pick out exactly what's going to happen to these planets. So here we can see that in our pre-industrial cases, the methane abundance can change by up to 2.4 times. And in the Archean cases, they change even more, by over a factor of 5. The ozone in the pre-industrial changes by over a factor of 4. And in our Archean Earth cases, ozone can change by almost a factor of 33 times between these different cases of stars. Now, one thing to notice is that the far to near UV ratio for the M4 here is much higher than it is for these other stars. And we can see that reflected. We can see the impact of that in the methane concentrations in our atmospheres. So methane builds up to the highest amounts when our planets are orbiting GJ876. And so this is basically just showing that spectral class and the type of UV radiation and this spectral slope here, basically characterizing this spectral slope of the UV of M-dwarf stars is pretty critical to pulling out the right atmospheric composition. And so we did a somewhat similar test with, looks like this got deleted. Sorry about that. But we did the next experiment that we did was that we took GJ876 and we modeled it at a few different ages. So we go from 650 million years all the way up to 5 billion years. You can see that on average, the amount of UV flux coming from the star is decreasing as the star ages. But as we showed in the previous plot, the F to NUV ratio of these stars are not linear with age. They're not linear and they're not monotonic. And so characterizing the spectral slope here is going to be just as, if not more important. And we can see that here in this bottom right plot. So methane changes, the methane concentrations change by over an order of magnitude here. I should note that these shaded regions bound the inner quartile ranges for stellar activity. And so this, for example, this red line represents the methane abundance at the median value, the median spectral, the medium spectra of the 5 billion year old star. but there is a range over which the star tends to vary, or stars like it tend to vary. And so I can see that over all of these ranges for each of these ages of stars, the methane abundance can increase by well over an order of magnitude. And the oxygen and ozone abundances also see quite a large difference, especially oxygen here. It seems I forgot to put in that this is our Archean Earth case. So sorry about that as well. But oxygen and ozone also see a strong change here. The main feature that I want to point out here in this reflectivity spectra is this ozone feature right here. So this is the ozone 0.26 micron feature. And we can see that as the star ages, so going from 650 million years in blue to 5 billion years in red, we are seeing, we are going from near saturation in the ozone feature to basically no ozone feature whatsoever once we hit about 3 billion years. And so this is something that telescopes like LUVAR or HABEX or the ELTs may be able to go after. And so if we were to detect this ozone feature around a planet that is around a young M-dwarf star, and we didn't understand the spectral character, the UV character of the star, then we may infer that there is a oxygen, something in the atmosphere of this planet is producing oxygen and eventually the ozone that is creating this feature. So this does look like a biosignature, but we've actually found that this O2, the O3 is ultimately a product of CO2 photolysis. As we can see here, the CO2 is being photolysed by FUV radiation, which is quite high for this very young M-dwarf. So as that CO2 gets photolysed, eventually it creates ozone here and creates this feature. So this constitutes a false positive biosignature. So I know that was quite a bit, but in order to summarize, there's a lot of things going on with stars that are impacting the planetary processes that are taking place. And it's very important for us to understand how these stellar processes are impacting planetary processes, especially when it comes to habitability. So to review, the high energy radiation and stellar winds can erode or even completely remove a terrestrial planet's atmosphere. However, that same activity could drive the photoevaporation of primordial envelopes, leaving terrestrial cores behind that may or may not have an atmosphere. We also noted that planets in the habitable zones of M-dwarfs can likely spend their adolescence in runaway greenhouse with large amounts of X-ray and extreme UV activity that can drive desiccation, hydrogen escape, and oxygen buildup. We also saw how magnetic activity from low-mass stars can actually accelerate instead of hinder the atmospheric escape processes. We also looked at how flares from active stars appear to only marginally impact composition, but flares accompanied with coronal mass ejections and particle events could spell destruction for ozone in the atmosphere and any chance for UV shielding of the surface. And lastly, we went over how relative amounts of far and near UV solar radiation drive complex photochemical networks in terrestrial atmospheres with the potential to create false positive biosignatures. So with that, I'd like to thank you for your time, and I hope you enjoy the rest of the conference.